Okay, welcome back. The purpose of this video is to show some applications of differential equations. We've seen, hopefully, in the previous videos that you can solve differential equations and you can make slope fields that help make graphical representations of the answers to differential equations. Now we'll look at some of the applications. And interestingly enough, with all this coronavirus garbage going on, causing us so much trouble, coronavirus actually makes an interesting use of differential equations and gives us a way of modeling how many people can get this and why it's so dangerous. But before we get to that, this warm-up, just kind of an interesting little exercise. If you want to try to think about the answer before I tell you, that's always a good idea because that's what I would do in class. Basically, it says in a lake, there's a patch of lily pads. Every day, the patch doubles in size. So you can picture there's a few of these pads covering the lake, and then it doubles, and then it doubles again, it doubles again. It says if it takes 48 days for the patch to cover the entire lake, so it grows large enough to cover the lake in 48 days, how long did it take the patch to cover only half the lake? So take a moment, think about it. And since the video, I'm just going to go on because you can pause it yourself if you want to think about an answer. Now, if you read it really carefully, the answer shouldn't be surprising, but I find a lot of people don't get the answer because they don't really have a good grasp of the level of growth that's going on here. So the answer is 47 days. In 47 days, it'll cover half the lake, and on the 48th day, it'll cover the entire lake. Now, that seems kind of surprising to some people because they're like, it really took all that time. It took 47 days to get it to only half, and then suddenly it covers the entire lake. But remember, it does say that every day the patch doubles in size. So on day 47, if it covered half the lake, it would then double the next day and cover the entire lake. So this is the idea of doubling and exponential growth, which we'll look at through the lens of differential equations. So if you said 47 days, good for you. You read carefully. If that surprises you, you can just think about the fact, it does double every day. So if it would, every time you go back a day, it's half the size. So it did take all that time to cover half the lake, but it only took the next day to double and cover the entire lake. All right. And it's this kind of growth that is actually related to all this coronavirus stuff, and we can look at it from a calculus perspective. All right. So the goal here is to be able to solve differential equation application problems. So now that you've seen what differential equations are and how to solve at least separable differential equations, we want to see how these equations can apply to solving things in real life. So I decided to go with this example because it was so pertinent to what's going on right now. So everything now is, oh no, the coronavirus, it's taken over everything. You look at the news and that's all they talk about, and rightfully so, right? It's completely changed our society in just a couple weeks here. So why is it such a problem? Well, I found a lot of information. There's a lot of data out there right now. And one of the things I found said that cases in the U.S. are currently doubling every 4 days. Even more scary, I found out, I think it was, I don't remember what website, but it was today that they said in New York, it's actually doubling every 3 days. Now, luckily, most of the cases are still restricted to New York City, but where our cases are growing even faster than the rest of the country. So cases are doubling in the U.S. every 4 days. This is equivalent to each person who has it basically passes it to another healthy person in a 4-day span. Now, obviously, as it's passing, this is on average. One person may not pass it to anybody, another person may pass it to 5 people. But for it to double every 4 days, it's equivalent to this. We could say that every person who has it has given it to another person within 4 days. So 4 days later, there's basically double the number of people who have it. Now, what this means for its growth is if only a few have it, only a few get it. If only like 3 people are infected, well, 4 days later, 3 more people have it, and there'll be a total of 6. The problem becomes that if a lot of people have it, a lot of people get it. So if 1 million people have it, 4 days later, another 1 million people will get it. So the amount that people, or the number of people who have it, is basically based on the number of people who had it before them. So however many people have it at a given time tells you how many people are going to get it, how much it's going to grow. And we can go down here. So to put it in terms of calculus, the rate at which we get new people with the virus is based on how many people have the virus. That's what this logic says. Now, this is related very much to calculus because rates of change are derivatives. So we can actually model the growth of the virus by using ideas from calculus, because it's the rate at which people are getting the virus that we care about. This is all that stuff about, oh, let's flatten the curve, which I'll show you. Everyone keeps saying flatten the curve, flatten the curve. They're really talking in calculus language. They want to change the derivative. They want to make the rate of change go down and essentially flatten. If the rate of change flattens, then no new people are getting it. But for now, we have the opposite problem. The rate of change is actually on the increase. So this rate, the derivative of the people function who have the disease, is based on how many people have it. So we can formulate this actually as a differential equation. But let me show you what does the growth rate of this look like. And it's a familiar thing. Here's the total cases, I believe, in the United States. And when first it started in China, we were hearing about everybody in China having it, but there weren't too many people in the United States. There was one person, I think, suddenly appeared in California. Then there was another case, I don't remember where that was, but it was somewhere else in the country. Then a couple appeared in New York City. Then there was a cruise ship. Then suddenly there was like 20-ish people who had it. And you notice here, very, very small numbers. But as time went on, you started hearing about not just dozens of people with it, but then there were hundreds of people and then thousands of people. And we're up to the point where we're at about 100,000 people. In fact, you could see why they decided to close the schools down. It was right around here that the announcement came out, and you could see that the curve just started to go kind of crazy here. There was nobody who had it. Within just a week or two, suddenly there were more cases, and this thing looks like it's about to shoot up a lot higher. So, and this only goes to March 14th. As of this recording, it's March 27th, and there's a lot more cases than this. But you might recognize this pattern as exponential growth. And exponential growth can be crazy. It's good if you're making money this way, but it's bad if people are getting infected with a disease by this pattern. Now, you learn how to handle exponential growth cases in other courses, but nowhere ever tells you why it's exponential growth and how they knew the formula that they did for exponential growth. So calculus is actually where all this stuff got developed. Even though they teach it to you in earlier courses, we'll now be able to develop and prove why an exponential curve, specifically one that has like e to the power or something, models growth like this, all right? Let's look at just a couple other ones. Here was one that they basically were trying to say, look, New York had passed France or whatever. I don't know why France was a big deal. But you could see New York's growth curve, and we've been, unfortunately, a hotbed for this coronavirus, at least downstate. And once again, nobody had it, nobody had very few cases. When you started hearing in New York, there was maybe a handful of people who had it just a few weeks ago. And then suddenly it exploded. And now, according to this thing's a little more recent, but on the 22nd, there were upwards of 20,000 cases. And something I looked at said I think we might even be up to maybe 80,000, I think, if I remember correctly. I was looking at a lot of different graphs. So I was thinking, we're approaching in New York alone 100,000 cases. So once again, this exponential growth curve is apparent. And then one more. Let's see if we can get it to go to the next screen here. There we go. China was sort of the beginnings of this horrible disease, and this was a model someone came up with in China, and this is how the model actually matched the real growth pattern. So someone early on had said this is how it should grow, and if you notice, the red dots actually match this person's growth model very, very closely. So you can see these are dates from January 16th to January 28th, and once again, this exponential growth curve. So this is why China had such a problem with it before it eventually worked its way over here into other countries like like Italy is currently also having a huge outbreak. All right. So how does calculus involve this? Well, we've talked about the growth rate of the disease. So with the growth rate being that it doubles every 4 days, I'm able to actually use that to project other values for other days, so long as the pattern continues, and I have some kind of starting condition. So I actually looked this up in another article. It says WHO. Who is it? I don't know. No, just kidding. WHO is the World Health Organization. And if you want more corny jokes, I once knew a doctor who worked for that organization. His name was Doctor Who. All right, I'll stop. So WHO, the World Health Organization, reported that there were 1,678 cases in the United States. I don't know why I have where. Should be were. That's what happens when you make a new. Oh, I got rid of the whole word, too. So they had that 1,678 people were infected as of March 15th. How many will be infected by the start of April? So I can actually solve this using a differential equation because I know the rate of change. I know the rate of change is based on the population, that if I wait 4 days, it will double the number of people who have it, so long as that pattern continues. Now, that pattern can't continue forever because then eventually everyone on Earth would have it. So there is a slowing down of the curve eventually because more and more people get infected and you run out of people to infect. But for now, we haven't even infected 1% of the population. So this exponential growth curve is going to run for a while, and it's actually going to be pretty accurate for a while longer. So using this information on the backboard, I'll show you how we can formulate a differential equation that will model what's going on based on all the information I got. And this is all real information online. And then we can make predictions about how many people will get this disease by a certain time, and then why everybody's freaked out, why schools have closed and they have done all the social distancing and they don't want people interacting because of how dangerous this growth can be. So let me show you the solution to it, and then do in general how we can model things with differential equations. So this particular example, I have all the work here because it's easier to just have it all up here than to try to write on it because I don't have this board attached to a wall, as you probably figured out. So I started in the upper left corner with dy dt equals 2y. Now, why did I come up with this? This is actually me interpreting the growth rate of the disease. So I should define my terms. So I do. I let y is the number of people who have the virus. And so that's what y will represent. And then I wanted to make the calculation a little easier because to jump every 4 days is a little annoying. So I said, we'll let 1 unit of t represent 4 days. So when t equals 1, that means 4 days have gone by. When t equals 2, that means 8 days have gone by. So it just makes my calculation a little easier to handle. So keep that in mind when I do t. T is basically a block of a 4-day time span. So now I can formulate maybe not what the original equation is yet, but I have its rate of change. How does the virus grow? What is the change of the virus? Well, it doubles every 4 days. So the change in the population, remember that's what dy means. So a change in the population over a change in time is based on the population itself. So how quickly does the population change with respect to a unit of time? Well, since I made a unit of time 4 days, the population changes in 4 days, it doubles. So it's double what the original population was. So this is how we can formulate into a differential equation. The change, how many more people get it over time, it's double the number of people who already have it. If you formulate this into a differential equation, you can now solve for what the original person equation is. What is the actual equation that predicts the number of people who will have this, all based on the rate of change. So this is the rate of change function. This is a separable differential equation. So I'll divide the y over to the dy and multiply the dt over to the 2. So after doing that, I get the separated equation 1 over y dy equals 2 times dt. Now, when you solve this, after you have it separated, you integrate both sides. When I integrate 1 over y, I get natural log of absolute value of y. When I integrate 2 with respect to t, that's why the dt is on there, the integral or antiderivative of 2 dt is 2t, and I put the plus c over here because I'm going to want to get the y by itself. I want to get the population function in terms of time. So to get rid of that natural log, remember the natural log has a little e on the bottom of it. You do that tornado thing. E to this power equals what's in front of the log. So that's from pre-calc and algebra 2. So to rewrite this, I get e to this power equals y. That's where I got this equation from. Now, I'm able to get rid of the absolute value bars because the population's always positive. We're not dealing with negative people. So there's no need to have that absolute value bar on there because basically the y can't be negative. So since the y's can't be negative, I'm going to ignore the absolute value bars. It's not necessary. So that's where the absolute value bar went. So I'm left with the equation y equals e to the 2t plus c. Now, I showed this in a previous video, but they normally simplify this a little further because e to the 2t plus c, this is equivalent to e to the 2t times e to the c. Remember, if you take like bases and multiply them, you can add the exponents. So this is going backwards from that. It's using the rule backwards that I can basically give e to the 2t and multiply it by e to the c. This is the same as this. So now that I've done this, this e to the c, remember c is some number. E to the c is another number. So what they do is instead of calling it e to the c, you can just replace it with another constant. So e to a constant is another constant. So the c is now representing whatever this would be. So in the end, you get this simpler equation. And this should look familiar because it looks like an exponential growth equation. So it proves that if the original equation was true, if the rate at which people are getting the disease is based on doubling the number of people who have the disease, the function that gives you the number of people who have the disease is an exponential function. It's namely some constant times e to the 2t. Now, since I want to actually answer a question for a given number of people at a given time, remember, Doctor Who and friends told us that 1,673 people had it on March 15th, and we want to know how many people would have it by the start of April. I can use that as my initial condition in the differential equation. So in the differential equation, I have y equals c e to the 2t, but I know that at time 0, I'll call March 15th times 0, that's my choice, so I'll just go we'll call that, the starting time. At time 0, the number of people who have it is 1,678. That lets me solve this because e times 2 to the 0 is e to the 0, and a number to the 0 is 1, and 1 times c is c. So c turns out to be 1,678. So there's my population equation based on what Who told me and the fact I know, somebody else told me it was doubling every 4 days. I now have an equation. Just keep in mind my t units. Every time I go up 1 t, I'm going up 4 days. But this equation, based on every 4 days that go by, will tell me how many people have the disease. So I want to know how many will have it by the start of April. So I put on the side the extra information. By the start of April, 16 days roughly will have passed because basically we need to get from the 15th through the 31st. By the time the 31st ends, that's about the 16th day. So it seemed best to use that number because now just be careful. 16 days is 4 units of t. Remember up here I had 1 unit of t was 4 days. So if 1 unit of t is 4 days, 4 units of t will be 16 days. So I don't want to plug in 16, I want to plug in 4 because those are my t units. But if I just make that little kind of annoying conversion, I'm able to answer the question because now I can put this in a calculator. I basically get 16e to the 2 times 4 of those units. And whatever this comes out as, which you've been looking at for a while, get 5,200,047.502. Remember, it's a model. It's roughly correct. Like if you looked at that, remember that China graph, they had the real values versus the predicted values, and it was a pretty darn good estimate. So what this tells us is by April 1st, there could be as many as 5 million people who have this disease. Kind of crazy to think that at the beginning of the month it was a handful of people, And now it's, like I said, I think as of today, it's gone up to about 100,000 throughout the country, or it's very close to that. And within the next few days, it could be as high as 5 million, which is kind of insane. This is why everyone's tried to do this social distancing stuff. This whole thing, closing school and everything, has been for the express purpose of trying to lower this rate. Because basically, if with it unabated, if somebody's giving it to somebody else every 4 days on average, if we keep people away from each other, this rate will go down. Maybe we'll only have one person give it every 10 days, or maybe it'll take 5 people to give it to one person instead of one person to give it to another. So the whole goal of this social distancing is to actually change the derivative, change the growth of how quickly people are getting it. If you change that growth, you change this formula, and you can bend this to get fewer people, which is what we want. In fact, if people don't listen to social distancing, this could go up, and this number could get worse. And then it takes only a short amount of time before everybody's got this thing. And the problem is the death rate of this disease is about 2 or 3%. Now, it's not so bad for young people like you, and it's not actually so bad for people who are closer to middle age like myself, but older people have a very high death rate from it. Overall, the population rate of death is about 2 to 3%. So if we let everyone in the country get it, we could be talking about as many as 6 million, 9 million deaths. So this is why it's become so important to try to limit this thing. Now, one other thing they've talked a lot about, which is funny because it's really calculus and a lot of people don't realize it, and it came up as I was searching this, was you hear all these people go, here's some of the data I found. Where is it? There we go. You keep seeing people go, oh, flatten the curve, flatten the curve. What do they talk about? And here, I didn't even put in flatten the curve. I just put coronavirus curve. And you can see all these, pictures. Here's flattening the curve. Because basically, it's going to exponentially grow. At some point, we're going to run out of people, and the thing will flatten and then go down. The reason they're trying to flatten the curve, which you see in all these little things here, upward trajectory or flattened curve, and there's, as I go down, there's more stuff about it. I think there's another one. There's a little, here it is. It's like a little animated thing about whatever. It's just like a flu or a cold. She's like, don't panic. Let's wash our hands and stay home. And you see that the curve flattens out. And their goal is to keep the exponential growth lower, so when the thing does start to finally abate, because obviously we don't have infinite people, it will eventually start going down, that we don't overload the capacity of our healthcare system. Now, when they say flatten the curve, everybody's talking calculus and they don't even realize it, because what are they talking about? They want the slope of this thing to go down. They want its derivative not to be as bad. So instead of having a derivative of 2y, we'd like the thing to have a derivative of maybe 0.5y or 0.1y. And that would make this thing grow a lot slower and let us get under control a lot faster. So it's funny that all these people are really talking calculus, and the professionals know they're doing it, but a lot of the people on the news don't know that they're actually speaking the language of calculus when they're talking about this disease. All right? So sort of a twist on the lesson, because I said I obviously didn't teach this last year this way because there was no coronavirus and no craziness, but I think it's kind of funny, it made a really good example for this. So hopefully you see this is how mathematical modeling can be used and how useful it is to let us know about trouble, because I said all the people started to get in action when they started to see that curve go up. Good thing people reacted what they did. In fact, had it been a little better, they would have reacted a little sooner. Every day that you wait is a day that is a disaster. So the sooner you do it, the sooner you save lives, and hopefully we'll be able to get it under control. All right, so instead of this morbid topic, let's look at something a little more standard. So now that I've shown you that example, we can go over how differential equations can model growth and decay. So you've learned about growth and decay formulas in the form of things like APERT and radioactive decay formulas, and they always have e to some power in them. The reason those formulas are the way they are comes from calculus. So exponential growth, which you saw hopefully through that example of the coronavirus, exponential growth occurs when the rate of increase is proportional to the amount present. In my example, the rate of increase was doubling every 4 days, so it was directly proportional to the amount present. Remember, if there's a small amount present, there was a small amount of growth. There were a lot of people who had it, there was a lot of growth. Basically, it was double in my example, but a small amount doubled is a small amount, a big amount doubled is a big amount. The more present, the more the growth. So the problem is when you double the population, you now have more people who have it, and then they double, and then you have more people who have it, and they double, and it starts to grow more, and the more you have, the more you get. Now, the way exponential growth is modeled is through this differential equation. Basically, if this is happening where the amount of growth is proportional to the amount present, dy dt will equal some number times y. The k is a constant. My constant for the coronavirus was what I looked up, doubling every 4 days. But this number could be anything. If it's positive, then it's a growth equation. And this thing just says, they use this y sub naught for the initial condition. So notice I found at time 0 what the population was, and I was able to use this after solving the differential equation. So exponential growth actually starts this way. It has a derivative of some kind of proportional constant growth based on the original amount. Now, if it's decay, something like you've seen exponential decay before in the form of like radioactive decay and things like that. Exponential decay is when the rate decreases in proportion to the amount present. Oh, I have so many typos in this. In proportion. There we go. So exponential decay is when the rate decreases in proportion to the amount present. The less that's present, the slower it depletes. So this happens with like radioactive plutonium. If you have like 5 grams of it, a certain amount will go away. As it lowers and it gets to be 1 gram, you lose less of it. That's why it takes so long for radioactive things to go away, because the less you have, the more slowly it depletes, and it takes a while for it to deplete to a level where it's not dangerous. If you're not growing, but you're shrinking, there's a negative on the K. So the K is technically still positive, but you're going to throw a negative on it. And basically, if there's a negative on here, that's going to represent a decay rate. So we would like this in cases where things are shrinking, because positive will make the positive growth, negative will make a negative growth, which will shrink the original amount. Now, when you solve this, you'll, instead of having in the power a positive number, you'll get a negative number in the power, and it'll actually make the equation shrink. All right. So it's important to read whether it's growth or decay. Obviously, in the case of coronavirus, it's growth, at least for now. Hopefully, we can eventually shrink it back down, but right now it's growth. I'll do one more growth example, and then one that's a little more standard and less morbid. And then we can move on, and I'll let you try one that's decay rate. And then there's a little more to do. I'll do an AP type question in the next video. And then that should cover pretty much everything for differential equations. It brings us very close to the end of the course. This is actually the last lesson I would have taught. I don't want to say this is the absolute last lesson I'll put out, because I do want to go back through all the AP stuff and just be careful that with their new test that I didn't miss anything. So this is the standard last lesson I do, so we're pretty much there. It's where we can start doing review. But just in case, I'm qualifying that there might be one more if I find anything that I missed. All right. So, well, let's just get this out of the way. So this is a more standard example. The current world population is 7.4 billion. Now, I'm not sure, I didn't really update it for this year. This might be a year or two old, but let's just say it's accurate. The current world population is 7.4 billion. The current growth rate is 1.13% per year. We'll assume that this is continuing. The funny part about this is, even though the world population keeps growing, it's getting pretty large, this number actually has slowly decreased over time. The world population is not growing at the rate it used to, so its derivative has kind of gone down. But this doesn't go down very much. We'll just assume for now that stays constant. So that's an assumption, but it hasn't changed really that much over the last 10, 20 years anyway. So assuming that the current world population is 7.4 billion, and this is the growth rate, 1.13% per year, how long will it take to reach 10 billion people? So if we formulate this in terms of a differential equation, a 1.13% per year growth rate means that however many people in the population, the next year you'll add on 1.13%. So basically the new population is based on the population you already have, and the growth rate is based on the number of people you already have. If you have 1,000 people, you're not going to get too many more. You're going to get 1.13% times that. If you have 1 billion people, well, then you're going to get more people out of this, because 1.13% of 1 billion is a lot more than 1.13% of 1,000. But basically, I'm going to formulate this like I did the coronavirus problem. We'll put in terms of a differential equation, solve that differential equation. Since it's a positive growth rate, we'll get a positive exponential growth function, and then we'll be able to use it to figure out how long it takes to reach 10 billion. So let me get that going. All right, so assuming all this stuff is true, I was sure, since it's a application problem, to assign my variables. I said let P be the world population. I decided to go in billions this time. That way I didn't have to write the number 7,400,000,000 out. So P is the world population in billions. At T being the number of years, we'll let T equals 0 be now, so the year 2020. So we'll say at time 0, which is now, year 2020, there's 7.4 billion people in the world. And anytime I use P, it's the number of people at the time T. So to formulate this, what does it mean to have a 1.13% growth rate? It means that what's the change of my population? My population change, so how many more people will there be? This doesn't count the original people. How many more people will there be? How much does it change per year? The number of people that I will grow is 0.0113 times the population I already have. That's what it means for it to grow at that rate. I took the percent and just turned it into a decimal. All right, so that's how I formulated this. The change in people over time is this percent times the number of people I have. And remember, the more people I have, the more my change will be. So once I've set up this differential equation, and it has that form I mentioned, dy over dx equals ky, with where k is some constant, the constant is the growth rate, that has that form. So this is going to be some kind of exponential growth formula. I can now determine it. So the important calculus part is to be able to get the formula from this. It's a separable differential equation, divide over the p, multiply over the dt, integrate both sides. Just like the other problem, 1 over p's antiderivative is natural log of absolute value of p. The integral of 0.0113 dt is going to be 0.0113t plus c. Now, when I go to solve for p, because I want a population function, just like I did last time, remember, it's e to this power will equal absolute value of p. And since p is population and it's never going to be negative, I got rid of the absolute value bars. So I don't need the absolute value bars anymore. And this is the rewrite of it in terms of p. So p by itself. From here, I did that simplification. E to some power plus c is e to some power, and then e to the 0.0113t plus c is e to the 0.0113t times e to the c. And e to the c is just a constant. So since e to the c is just another number, they just replace that and call it c to make it easier. So I get p equals c e to the 0.0113t. That's my general growth formula with the rate plugged in, but I want the specific one where I've solved for the c, so I'll use my initial condition. Remember, at time 0, the population 7.4. If I plug in time 0 and population 7.4, I can solve that c is 7.1, and then I get my actual population function. So I can predict the population of the world so long as I put in the number of years from 20 to this year, 2020. And it would actually work backwards too, so long as the model holds. If I put in negative numbers, if I want to know what the population was in 2015, I could put in -5. If I want to know what the population is going to be in 2025, I'll put in +5. Now, they didn't ask me what's the population at a given time. They want to know when the population reaches 10 billion. So I need to solve for t. Now, the rest of this is basically like pre-calculus exponentials unit. So once I have this equation that was derived from a differential equation, I now can solve it in a pre-calculus manner. Basically, I want to know at what time the population's 10, plug in the 10 for population, and then this thing needs to get solved for t. To solve it for t, to remind you, as you divide, you have to get to that t. That 7.4's got to go first. Divide off the 7.4. I got 1.35135 e to the 0.0113t. Now, the way I get rid of the e is to natural log both of these. If I natural log this, well, this is some number I would want to get out of a calculator. If I natural log this, remember throwing natural log in it lets me use the log rule to kick that thing out. So the 0.0113t comes out front, and I get I didn't write it because I was running out of space. I get 0.0113t lne. lne is 1 because lne means e to what power gives me e, and that just cancels away as a 1. So in the next line, this hops out, lne goes away as 1, and I'm left with this line, and then all I need to do is divide this 0.0113 over off of the t. Oh, I know I have the t here. Get rid of that. On both sides. That's silly. So just divide that 0.0113 on both sides, and then you'll get what t is. I just threw all this into a calculator, and I got the number 26.64 years. So basically, when will the world population, according to this model, reach 10 billion? It'll happen in 26.64 years, roughly sometime in the year 2046. So coming up, but not too soon, but in the not too distant future, right? It's not, we'll all hopefully be alive then if Corona doesn't get us. All right. So this is a standard problem, basically using the differential equation, being able to make this interpretation at the beginning about the growth rate to turn it into an exponential equation that you've solved in previous courses. So this video is getting to be the length of a class, so I'd like to get it over with so you can take a break if you're watching the whole thing. I'll leave you with this problem that you can try. So the exciting new chemical, mathnium. Yeah, good old mathnium. This is a decay problem. It decays at a rate that in 1 year changes 100 grams into 98 grams. If you start with a sample of 525 grams of mathnium, and then it asks for a couple of questions. It first wants you to find the rate of decay. In the other problems, I gave the growth rates. This is actually going to be a decay rate. So be careful to figure out what percent it's decreased by. It started out at 100 and then dropped to 98. So see if you can figure out what the percent decrease was. It decreased by a certain percent. If you figure that out, you'll be able to set up the differential equation. So it says find the decay rate, which is a percentage or a decimal. Once you find that, see if you can set up the differential equation modeling the situation. And then finally, find how long until the 525 grams decays into just 500 grams. So once you have your equation, you should be able to do this. To give you a little hint, once you get that decay rate, because I've been just doing growth, this is going to be the model that you're going to work with. Once you get that rate, just make sure it's negative, then you should be able to solve the differential equation. So that's the little hint for you. All right, so see if you can solve that. I will start the next video with the solution to this, and then I've got a little bit harder AP problem to do, and then this lesson will be done.